Today we're going to look at exponentials and logarithms, and we need to do a little bit of preliminary work before we get into the actual work of it. And if we take a look here at this first problem, it says, as a society, we are accustomed to performing an action and then undoing or reversing that action. So if we reverse or undo putting on a jacket, what is it? Taking it off. Or if we open a door, if we reverse or undo that action, we're closing. Close the door. And we actually have that same idea in math. In math, we also find it useful to be able to undo certain actions, like adding 5 to a number. Well, what's the undoing or reversing of adding 5 to a number? Subtracting. Subtract 5. Or if we multiply a number by 4, what's our undoing? We're going to divide. Maybe a little bit tougher one, but how do we undo squaring a number? Square root. Good. And then the last one maybe really is a tougher one. We don't necessarily think of it in terms of undoing, but if we do the distributive property, when we undo that, what we're really doing is we're factoring. And what we call this in math, we say that addition and subtraction, or multiplication and division, or square rooting and squaring, they're called inverse operations, because one operation undoes the other, and I'm not sure that's a word. Also, factoring and distributive property, those undo each other, so they're inverse operations. And luckily we've done a unit on inverses, so we have a little bit of background. And that's what's here in this next, well, I still want to do this example. Inverse operations in mathematics helps us to solve equations. We want to consider the equation 2x plus 3 equals 35. And what we want to do first is we want to list the actions that are happening to x. So some of you are thinking, well, what is she talking about? And really, here's the actions. X is multiplied by 2. That's one thing that's happening to x, multiplied by 2. And then the other thing that's happening to x is that we're adding 3. And 3 is f. That's what's happening to add. Oh, good, I said it right. Well, to look at the reverse of these steps, I think it might be easier maybe to actually solve this equation. What are we going to do first? When we have 2x plus 3 equals 35, Megan, let's subtract 3. So we get 2x equals 32. That's one of the actions that we did to reverse. We subtracted 3. And then to finish this equation, it's 2 times x equals 32. How do we undo that multiplication? We're going to divide. And that's going to be the other action that's taking. We're dividing by 2. And when we finish this problem, by the way, we end up with x equals 16. So So we've used this idea of inverse operations even though that word might not have been used. What we did earlier in the unit that I'm going to skip here is how do we find the inverse of a function? And so I was going to have us go through that, but I don't want to go too fast over the rest of this, so I'm going to skip this here. If we have time at the end, we'll come back and do this one. But let's flip our papers over. But what is the underlying idea behind inverses? When we originally found inverses of functions this year, we always switched x and y. The x became the y became the x. But what we've been working with this week is some graphing of the functions. I'm going to just make my graph a little bit bigger. I'm sorry, it's really small, and I will still struggle to have it graphed with the disorientation. But what we did on Monday, earlier this week, is we graphed f of x equals 2 to the x. And we could rush through our notes and we could pull them out from before. But the bottom line is, what we did is we found that when we took 2 to the negative second, we came up with 0.25. And 2 to the negative first, we came up with 0.5. And 2 to the 0 is 1. And 2 to the first is 2. And 2 squared is 4. And 2 cubed is 8. And 2 to the fourth is 16. Which is going to go a little bit off our graph here, but let's do the best we can to graph those values. So negative 2 is 0.25. And negative 1 is 0.5. Then we have 0, 1, 1, 2, 2, 4, 3, 8, and 4, 16, which goes off our graph just a little bit. But if you typed it into your calculator, the picture will look roughly like that. And what we also talked about earlier in the week is it says for f of x, there appears to be an asymptote. An asymptote is a line that the graph approaches but never quite touches. And in this particular case, it's right here. In that kind of purplish colored line, notice that we crossed the x-axis. Sorry, we crossed the y-axis and we get y equals 0. It's a line that we keep getting closer and closer and closer to, but we never quite touch. Well, once we get that, that's what we did earlier in the week. Now what we're going to do is we're going to do the inverse of that. In the inverse, we switch the x's and the y's. So negative 2, negative 1, 0, 1, 2, 3, 4, over here in the y category. And then we have 0.25, 0.5, 1, 2, 4, 8, and 16. Reading from the previous table. All that I did is I switched those values. Negative 2.25 becomes 0.25, negative 2. Negative 1.5 becomes 0.5, negative 1, and so forth. And what we're going to do now is we're going to graph this, and again, do the best that you can, and I will do the same. 0.25 is negative 2. And 0.5 is negative 1. And then we have 1, 0, 2, 2, 1, 4, 2, 8, 3, and 16, 4, which is going to go off our graph just a little bit. But here's our picture. And in this particular case, we also have an asymptote. And we switched x and y. So in our original equation, we had y equals 0. So this time what it's going to be is, it's going to be x equals 0. And in fact, I'm going to erase that and write it in green because that's the color that I'm going to graph it in. But we have y equals 0 for the original. This one's going to be x equals 0. Which is roughly there. We'll see if I can scoot it over. Close enough. Again, we switched the x's and y's to graph the function, which means for our asymptotes, we're going to switch as well. We had y in that purplish color, now we have x. An asymptote is a line that the graph approaches but never quite touches. There's two functions. These two functions reflect over a line. And excellent. That somebody remembers. I think that you can expect to see that on your exam. So any of the Algebra 2 classes this year, I think you can expect to see that on the exam. I'm pretty sure we put it on there last year. Where that graphs, if you recall, is from the lower left to the upper right, and it goes through 0, 0. And if you think about it, what happens here is if we fold our graph along that black dotted line, that red graph is going to land on that blue graph, exactly. But you have to fold it along that black dotted line. Let's look at another one here on the same page. And luckily, we've also graphed f of x equals 3 to the x. We did that earlier in the week. And the values that we found here were -2 is 0.11, -1 is 0.33, 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9. And by the way, you can go to your calculator here and you can type it in. And here comes the picture. Or even better, maybe, is getting the table. There's the values. We just went to y equals, and then we did second graph to get to our table. You did the best you can, and I will do the same. I'm going to try to make this grid a little bit bigger. And we have -2.11, -1, 0.33, 0, 1, 1, 3, 2, 9. And notice that it's just a little bit steeper than the one we did before, but it's still an increasing function. And then what we want to do is we want to do the inverse. But by the way, is there an asymptote on this one? Well, it's the same as it was before. We have that asymptote at y equals 0. So the question is, are we going to have an asymptote for our inverse graph at x equals 0 as I fill it in? And one of the reasons that I know is because 2 to the x and 3 to the x aren't very different. But what we're graphing here in the second one is just the inverse. We switch the x and the y. We switch the x and the y. And then we're going to graph. So 0.11, negative 2. 0.33, negative 1. 1, 0. 3, 1. And 9, 2. 6, 3, 4, 5, 6, 7, 8, 9. 2. But like I said, if you compare back to the one above, we can hardly tell the difference. Because there's not that much difference. And we do have an asymptote. This time it happens to be a vertical asymptote. That's our green asymptote. An asymptote being a line that the graph approaches but never quite touches. And some of you again are noticing these two lines reflect over that line, y equals x. And when we draw that in, it goes from the lower left to the upper right, and we go up here, and we go through 0, 0. But one of the things that happens when we draw that in is it gives us a good visual image. If we fold this graph along that black dotted line, will the red graph land on the blue graph? And it will. So let's see if we can kind of pull this all together, come up with a couple of characteristics of these graphs as we flip our page over. And what we just graphed, these inverse that we just graphed have a special name, and it's kind of goofy, and sometimes because it's such a long word, people think that it's hard. It's just funny looking, that's all it is. And the name of these inverse is called logarithm. It's Logarithms. Logarithms. That's all it is. It's the inverse of an exponential function. So it's easy for me to flip back. We want to come up. Oh, by the way, the abbreviation for logarithm is LOG. But let's flip back, and it's easy for me. You don't have to keep flipping your paper back and forth. It says y-intercepts. When we look back, we're looking at the red graph. Well, our red graph never touches the y-axis on example 6. And our red graph never touches the y-axis on number 5 either. Which must mean that we don't have a y-intercept. But if we go back here, again on number 5, what's our x-intercept? Well, where does the graph cross the x-axis? Looks like it crosses at 1, 0. I wonder if that's true for number 6. 1, 0. The general trend of both graphs, starting at the left, we go up, 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 up. There's an increasing trend. Our domain of our graph. Again, we're looking at the red graph on my screen. The red graph can't break through that green dotted line. It's a solid figure that we're never going to cross. We're not going to touch it either. And because of that, our domain is going to be everything to the right of that green line. In interval notation, that means that it's going to be from 0 to infinity. Our range, however, is not limited. Again, if we just look at one particular graph, it doesn't matter which one, we've got values of y that are below the x-axis. We've got values of y that are above the x-axis. We've got a value of y that's 0. So in this particular case, and all here, our range of this function is all reals. Y is allowed to be any value. It can be a positive number, it can be a negative number, it can be a fraction, it can be a decimal, it can be a radical, it can be zero. So there's some characteristics of the logarithm. And we're going to be working with more of the logarithm starting tomorrow, which is really Monday. But let's just do a little bit of the basics here, and then we'll get back into it on Monday. But let's see. Working algebraically, finding the inverse functions of exponentials and logarithms. So first of all, for an exponential function, y equals b to the x, its inverse is log base b of x equals y. So by the way, our inverse of this function, remember, we switched the x and y. So this would have been x equals b to the y when we switched our x and y. So its inverse function is this. Number 7. So how does that really work? Using the definition of logarithm, let's try to write the equations for inverses that we found in examples number 5 and 6. Remember to write f of x as y to start. So when we start over here, f of x is y equals 2 to the x. Well, once again, what we're going to do is we're going to switch the x and the y. And I'm going to write it over here on the line. So x equals 2 to the y. We switched the x and the y. And then I'm getting a little bit ahead of myself, but I think it might be easier for you to understand if I say it anyway. All that a logarithm is another way to write an exponential. So whatever a logarithm equals is the exponent. So when we write this here, this one's going to be log base 2 of x equals y. I'm going to say it again, and I'm getting ahead of myself. I'm getting to Monday already. A logarithm is another way of writing an exponent. So from our exponential over here, x equals 2 to the y, the exponent equals y, so that's what the logarithm equals. Let's try this last one here before we go back and fill in our answers for 5 and 6. F of x, another way to write f of x is y equals 3 to the x. That was our second function that we dealt with, that we graphed. And when we're doing this, we're going to switch the x and the y. So x goes where y went, and y goes where x went. A logarithm is another way of writing an exponent. So when we write this here, the exponent of this inverse, which is y, is what our logarithm is going to equal. And this one's log base 3 of x. So finally, let's flip our papers back and we can fill those in. Here's number 5. What we just said. This one is log base 2 of x equals y. That's what we said it was. We switched the x and the y. And on number 3 here, oh, I don't do that. We get log base 3 of x equals 1.